Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion. We're looking at the third day of Galileo's Dialogues Concerning Two New Sciences. This brought us up to about page 133 or 134 in a Student's Guide to the Great Physics Text, Volume 2. You might recall in our last lecture, we ended by looking at figure 10.2. What is the question that Galileo is considering here? He's considering the situation that you have some object, like a block or a mass of some sort, resting on a ramp. That block is represented by the letter G in this diagram. The ramp has a pulley at the top, located at location F, and there's another mass, H, that is attached to mass G via a string passing over the pulley. And the question that's being asked is, how much weight does it take to balance the object G on the ramp? Now you might imagine that the steeper the ramp, the more weight it's going to take in order to hold it up, and you'd be correct. And that's kind of a common sense observation. And the shallower the ramp, that is, the more flat it is, the less weight is going to have to be hung from point H in order to balance it. But what we've done is we've looked at how Galileo was able to come up with a formula for how much weight it requires to balance that mass G. In fact, it's not something that Galileo came up with. He drew on the work of Simon Stevinus. So we spent some time last time talking about the work of Simon Stevinus and how he arrived at a formula for the mass required to balance another mass on a ramp. The formula that we came up with is to say that the ratio of the weights at G and H happens to be equal to the ratio of the lengths of the ramp segments FA and FC. So in particular, if we were to draw this ramp like this, if this point is A, and this point is F, and this point is C, and we wanted to know how much weight, I'll call this point weight G, and another weight, this would be weight H, and we had this pulley placed right here, and we wanted to know what the weight H is that would balance weight G. Well, the formula is that weight G is balanced by a weight H if the ratio of those weights is equal to the length of the line segment FA to the line segment FC. What we're really saying here is that it depends on the slope of the ramp. So you might imagine as FC gets smaller and smaller and smaller, if FA to remain the same, then that ramp would be shallower and shallower and shallower. And so the weight it would take to balance weight G would be less and less and less. This is the formula that Galileo presented us with and we talked about in the last section. So let's do a couple of example problems to make sure we understand how to apply this. Okay? So I'm going to draw a couple of triangles here. So let's imagine we have a ramp like this. And this side is of length 2, and this side is of length 4. And once again, we have this pulley right here. And let's suppose we were to place these two masses, one right here, and let's suppose that this one has a mass of 4. And the question is, what is the mass that must be hung right here? I'll call that mass A. How much mass would be required in order to balance the mass 4? Okay, so here's the question. How much mass, or weight, you might say, if we wanted to use weight instead, is required to hold the block on the ramp in equilibrium? That is, so that it does not slide down the ramp. And the answer in this case, the weight of block A, as you probably guessed, would be 2. So the ratio of 4 to weight A is the same as the ratio of those lengths right there, 4 and 2. Okay, let's do another one. That was pretty easy. Let's suppose that we have a different ramp. This one is a bit shallower slope. Once again, it has an altitude of 2. And let's suppose that this has a length of 8. Once again, I ask how much weight, if I had a mass of 4, or a weight of 4 resting on this ramp, and I have a pulley like this, and I were to hang another mass right here, let's call this mass B, how much would be required in order to balance that mass of 4? Well, you can probably guess that it's going to require less mass. Why? Well, because this is a shallower ramp. It's less likely to slide down, and so it's going to take less weight to support it. And once again, we know the ratio, the weight of B, is going to have to be, in this case, 1. Because there's a 1 to 4 ratio between 8 and 2, therefore there must be a 1 to 4 ratio in the weights that will balance one another. And we'll do one more just for good measure. Let's say we have a very shallow ramp like this. Doesn't look very good, but let's suppose that this once again has a length of 2, and that has a length of 16. And once again, we put a mass on it, and let's suppose this is once again a mass of 4. And once again, we ask how much weight do we have to hang over here so that weight 4 does not slide down. Let's call this mass or weight C. And you might guess the weight C, well, there's a 16 to 2 ratio of the lengths, or 8 to 1. So there must be an 8 to 1 ratio of this weight to weight C. And so weight C has to have a weight of 1/2. And this could be pounds or newtons or whatever kind of unit you want to use. But the important point is it's an 8 to 1 ratio. Okay, so far we've been talking about the weights that are required in order to hold something in equilibrium on a ramp. But that's not the main point that Galileo is making. What he's really getting at is he wants to talk about the acceleration that this block will have if this cord is cut and it's allowed to slide down the ramp. And the main point that Galileo is making is that the acceleration, or this is where he's going with this, the acceleration of the block down the ramp if the string were cut he says is proportional to the force that was required to support it. Okay, so in other words, the acceleration, the subsequent acceleration, is proportional to the force of restraint. Okay, so let's do an example problem here. A couple of example problems. Let me go back to these situations, the exact same situations, and let's suppose that I were to tell you, let me number these, we'll call this case 1, case 2, and case 3. So if the 3 strings were cut, what would be the accelerations of these blocks down the ramp? Okay, and in order to solve this problem, we need to give you a little bit more information. So let's suppose that I were to tell you that if you cut string 1, so in case 1, the acceleration of this block in case A, the acceleration is going to be, let's just say it's 2. That could be 2 meters per second squared or 2 inches per second squared, but let's just say it has a value of 2 if you cut this. If I tell you this, then we can figure out what the acceleration of the block is in case 2. In case 2, well, because it took twice as much force to hold up the block in case 1 as in case 2, that means the acceleration in case 2 would just be 1. It would be half as big because it took half as much force to hold it up. What about in case 3? Well, the acceleration in case 3 would be 1/2, because this is 1/2 of the weight of this, and so since the acceleration that it feels is proportional to the force that it took to hold it up, the acceleration would be 1/2. If, on the other hand, I were to tell you, well, the acceleration in case 1, let's suppose, was 8, then we would know that in case 2, that the acceleration would be half of that. It would be 4, and the acceleration in case 3 would be 2. Okay? All right, so tell you what, we're out of room. We'll stop there, and we'll pick this up next time.